Why would a major manufacturer trust the shape of a raindrop over the advice of the experts? The piece, published on 8 July 2026, uses the history of the B-24 Liberator to ask how innovation actually happens. While the aeronautical establishment of the 1930s relied on a catalog of proven designs, a self-taught freelancer named David Davis looked at falling water droplets and saw a different path. The story follows the friction between credentialed experts and a stubborn outsider, offering a reminder that the most significant technological leaps often come from those who aren't afraid to trust their own eyes over the industry standard. Written by Mike Benitez in War on the Rocks, narrated for Arva. Join War on the Rocks and gain access to content trusted by policymakers, military leaders, and strategic thinkers worldwide. The most produced American military aircraft of World War II was not a small fighter, a trainer, or a simple utility airplane. It was a complex four-engine heavy bomber called the B-24 Liberator. Over the course of 5 years, American industry produced a staggering 18,482 of these bombers, and they served in every theater of the war. The B-24 was a workhorse with strategic impact, but it would not have had its utility or possibly even existed were it not for its wing. Of course, all airplanes need a wing to fly, but the B-24 Liberator's wing was special, an innovative oddity that enabled the B-24 to outperform the B-17 in speed, range, and useful load. It's also a distinctly American story of defense innovation, in which a self-taught engineer saw something the credentialed experts missed, relentlessly pushed his innovation until it overcame skeptics, and found a company with a hard problem and enough ambition to risk capital on a technological advantage. This is that story. In the 1930s, Consolidated Aircraft was a flying boat company, producing PBY Catalinas and PB-2Y Coronados with an inherent engineering challenge. Flying boats needed to unstick from the water efficiently, while also maximizing flight performance, which required a wing that generated considerable lift at low angles of attack. In 1937, Texas freelancer David R. Davis approached Consolidated with a revolutionary wing design that promised greater efficiency than any other wing in existence, with attributes that would solve the flying boat problem. Unlike all wings of the time, the so-called Davis wing was based on intuition, keen observation, and empirical evidence. Davis got his idea from watching falling water droplets. As the drops fell, he observed that they assumed the natural aerodynamic form of a teardrop. Starting with a perfect teardrop-shaped airfoil, Davis continually tweaked it until it produced lift, characterized it with a formula, and then refined it to maximize lift. In 1934, he was granted a patent for this fluid foil, claiming that this thick, low-drag airfoil could support a long, high-aspect ratio wing that was highly efficient. Potentially. To prove it, the wing had to be built, and that was a problem. As a freelancer, Davis had no resources to build a full-scale wing, let alone an airplane, so he needed an aircraft builder. But the idea faced heavy skepticism from every institution he approached for several reasons. Davis was a self-taught, self-titled practical engineer, not a credentialed aerodynamist. He also guarded the formula and coefficients behind his patented wing, fearing they would be stolen before he could profit from them. That made his claim hard to evaluate. He was asking an airplane manufacturer to trust a shape whose performance he would not fully disclose. Furthermore, educated engineers could not discern a scientific basis for why the unusual airfoil would perform as empirically claimed. A federal research institution, the National Advisory Committee on Aeronautics, had already charted the orderly path to advance the aviation industry. They had recently wind tunnel tested, characterized, and cataloged 78 proven airfoils for engineers to use to help them build better-performing aircraft. Davis had brought an empirical invention to Consolidated, and it looked nothing like any of the open-source industry standards that had already been rigorously evaluated by the premier aeronautical engineering body in the country. After some deliberation, in September 1937, Consolidated Aircraft decided to fund a subscale wind tunnel test to assess the Davis wing, and the results were so good that the test was thought to be a fluke or a calibration error. Consolidated was interested, but still not committed. When a new high-fidelity wind tunnel opened in August 1938, The tests were repeated side by side using a comparable-sized traditional airfoil. The Davis wing showed 20% better performance, and Consolidated committed to funding a full-scale flying demonstrator. The wing was incorporated into the XP-4Y1 Corregidor prototype, a proposed flying boat successor to the company's PBY Catalina. The improved performance was immediately noticeable, and Consolidated decided the Davis wing was the perfect technology to incorporate into a secret company project called Model 32, a land-based bomber project to best the B-17 Flying Fortress. The bomber project grew from the Army Air Corps' pre-war effort to expand its heavy bomber force as conflict approached. In early 1939, the Air Corps asked Consolidated to build the B-17 under license. After examining Boeing's aircraft, company president Reuben Fleet offered a more ambitious alternative: combine Consolidated's flying boat experience with the Davis wing to create a bomber that could fly farther while carrying more bombs. The Air Corps accepted the gamble, and Consolidated raced to turn the Model 32 into a flying prototype designated the XB-24. The XB-24 was a new aircraft that wed the radical wing with a familiar architecture. The bomber's slab-sided fuselage, high-mounted wing arrangement, four-engine layout, and twin tail were direct carryovers from Consolidated's flying boats. The XB-24 then incorporated novel features such as roller-type bomb bay doors and tricycle landing gear, the first for a heavy bomber, and was subsequently designated the B-24 Liberator. But the wing set it apart. Though they did not know why, Consolidated understood that the Davis wing's advantage depended on preserving smooth airflow, so they purposefully maximized it. The four engines were mounted low to minimize disruption across the upper wing surface. Instead of conventional circular pods, their nacelles were shaped as flattened, rounded rectangles that further reduced interference with the boundary layer flowing aft over the chord. The same logic extended to the skin. The B-24 used flush rivets in the top of the wing, reducing the small disturbances that could spoil its low-drag behavior. There was one more important detail about the wing. Its unique shape resulted in an unusually thick wing, which had a notable byproduct. It could carry more fuel than a similar-sized conventional wing. Collectively, this made the difference. Despite its inelegance and sensitivity to loading, icing, damage, and handling techniques, the B-24 generally flew faster, farther, and carried a more useful load than the B-17. This operational reach made it valuable over the Atlantic, the Pacific, North Africa, Europe, and Asia, a utility that drove production demand. Even though the Flying Fortress had a 4-year head start in production, nearly 6,000 more B-24s were produced than B-17s. Davis was later paid handsomely for his innovation. He licensed the wing to Consolidated in 1938 under an unusual royalty arrangement tied to each aircraft sold. The arrangement called for $2,500 per prototype and a sales-based royalty of 0.5% of the price of each bomber, with step-downs as a function of sales. Once his royalties exceeded $50,000, the fee would bottom out at 1/16%, 0.0625% per aircraft, roughly $90 per plane, or $2,000 in today's money. But no one had anticipated how useful the aircraft would be in World War II. By 1943, over 2,000 bombers had been sold, and Davis had earned over $200,000. Knowing how many more bombers were going to be built, the U.S. government intervened, and in April 1943 reduced his subsequent royalty to $5 per airplane. That said, with 18,482 B-24s built over 5 years, all equipped with his unique wing, David Davis made $400,000, $9 million today. What Davis had stumbled into was extending the laminar flow over an airfoil by preserving smooth airflow farther aft along the wing chord than any other wing. Laminar flow is a phenomenon that occurs when a fluid moves in smooth parallel layers with minimal to no mixing. The byproduct of laminar flow is low drag, and the byproduct of that in a wing is more efficient performance. By extending the wing thickness farther aft along the chord and making the taper as gradual as possible, Davis unintentionally increased the laminar flow surface area, resulting in improved performance. The wing worked before the institutions of aeronautics could say why it worked, a case of solution engineering running ahead of science. But there was soon an explanatory framework being built almost simultaneously from the very federal research establishment Davis had bypassed.
Along with aircraft company partnerships, the National Advisory Committee on Aeronautics had been attacking the same frontier from the opposite approach. Advances in low-turbulence wind tunnels allowed airfoil testing under cleaner conditions, where the boundary layer could be better studied. In 1939, a company called North American Aviation had been collaborating on the first National Advisory Committee on Aeronautics laminar airfoil in these wind tunnels. In the summer of 1940, facing a very compressed development schedule, they elected to incorporate this brand new National Advisory Committee on Aeronautics 45-100 laminar flow airfoil into the wing for its new pursuit fighter, the legendary P-51 Mustang. While the P-51 was not a Davis wing descendant, it represented the establishment's scientific answer to the same problem Davis had reached empirically through intuition, secrecy, and trial. The National Advisory Committee on Aeronautics pursued the same promise through theory, instrumentation, and repeatable public research. The Davis wing did not create the laminar flow revolution, but it arrived at that moment. The Davis wing performed best with a smooth, carefully finished surface. Later tests showed that small amounts of leading-edge roughness significantly increased its drag, suggesting that its wind tunnel advantage was difficult to reproduce fully under operational conditions. Its legacy is not the airfoil, but the entire aircraft designed around it. A high aspect ratio wing, unusually smooth construction, flush rivets, low-mounted engines, flattened nacelles, and careful attention to preserving clean flow over the upper wing surface. Davis also, counterintuitively, showed that an abnormally thick wing could still be quite efficient, and that thickness was extremely useful for storing additional fuel. Like the bomber that carried it, the Davis wing was far from perfect. It did not become a template for airfoils, nor was the wing used beyond Consolidated's wartime aircraft. Faster aircraft, compressibility effects, thinner wings, swept wings, and newer airfoils overtook it. But the question David Davis explored remained. How much performance is hidden in the manipulation of airflow itself? That question shaped post-war aeronautics, where curiosity, practical experimentation, and science converged in the jet age to uncover new frontiers of performance. This continual pursuit of improved airflow persists today, and even extends beyond aviation to things such as windmills and air conditioning ducting. But the Davis story remains the remarkable, uniquely American story of a self-taught engineer whose vision paid off for the country, the company, and the entrepreneur. Mike Benitez is the CEO of Purple Rhombus, a defense startup focused on the industrial-scale production of attritable unmanned aerial systems. Image, United States Air Force via Wikimedia Commons.